So now let's take a look at the stereochemistry of electrophilic addition reactions. So remember that an electrophilic addition reaction generates a reactive intermediate, which is a carbocation. And carbocations have a trigonal planar geometry. So that means that a nucleophile can attack on either side of the plane with equal probability. And so sometimes new stereogenic centers are formed from hydrohalogenation because of this. So let's take a look at this one example shown here. So here we have 1,3,3-trimethylcyclohexene, which is an achiral starting material, reacting with hydrochloric acid. So according to the Markovnikov rule, the hydrogen will bond to the less substituted carbon atom, and then the chlorine atom will bond to the more substituted carbon atom. And so what we have is 1-chloro-1,3,3-trimethylcyclohexane. And because this carbon right here that's bonded to the chlorine atom is a chiral center or a stereogenic center, we have to take into account stereochemistry. And so we get a combination of products. 2 enantiomers will be formed. So that means that we have a racemic mixture here, racemization. Molecule A here has the S configuration and molecule B has the R configuration. Again, the very first step is the attack of the alkene. So the alkene here is acting as a Lewis base, attacking this electron-deficient hydrogen atom. And this results in the cleavage of the sigma bond between the hydrogen and the chlorine atom. And so what we have here is the formation of the sigma bond between the carbon and the hydrogen atom, and the formation of a positive charge, a carbocation. So what we have here is a tertiary carbocation. And so now this chloride ion that was generated during the first step is acting as a nucleophile, which would then attack this carbocation on either side of the plane. So the chloride ion can attack above or below the plane. And again, for the second step, you can see that the nucleophile can attack on either side of the plane, above or below the plane, with equal probability. And so what we have here is racemization, a combination of 2 enantiomers with equal concentration. So we have a syn addition in which the hydrogen and the chlorine atom are on the same side of the plane, or anti-addition in which the 2 elements, hydrogen and the chlorine atoms, are on opposite sides of the plane. And here's the table that summarizes the electrophilic addition of hydrogen halide to alkenes. In terms of mechanism, the mechanism involves 2 steps, in which the first step is the formation of the carbocation, and rearrangement is possible. And then the second step is the attack of the nucleophile, which is the halide ion. In terms of regioselectivity, we have to follow Markovnikov's rule for unsymmetrical alkenes, in which the hydrogen is bonded to the less substituted carbon atom, and then the halogen, the halide ion, bonds to the more substituted carbon atom. And then finally, in terms of stereochemistry, syn and anti-addition occur at the stereogenic center. So here's practice problem number 19. Draw the products, including stereochemistry, of each reaction. So for the first one here, we have this alkene reacting with hydrogen bromide. So the very first step here is the formation of the carbocation. And so when you analyze this carbocation here, you can see that this is a stereogenic center because it has 1, 2, 3 different groups of atoms. And so what we have here is a stereogenic center. And so when we draw the final product here, the alkyl halide, there's going to be a stereochemistry at this chiral center. And so what we get is a combination of enantiomers. So the bromide ion will attack this carbocation here, which results in the formation of 2 enantiomers, in which the bromide ion or the bromine atom is facing towards the front, and then the other enantiomer has the bromine atom facing towards the back. And for the second reaction here, we have a dimethylcyclohexene reacting with hydrogen chloride. So again, the very first step in this reaction is the generation of the carbocation, followed by the nucleophilic attack, which is the chloride ion. So it will attack this electron-deficient carbocation, which generates this first product right here. So the chlorine atom is oriented towards the back. And then the second possible product here has the chlorine atom oriented towards the front. And so by analyzing these 2 structures over here, you can see that they're actually not enantiomers, but rather diastereomers. And again, the reason why is because they are not mirror images, but they're also non-superimposable. And so that's the very definition of the isostereomers, which is different from enantiomers. So we just looked at hydrohalogenation. So now let's take a look at hydration and halogenation. In a hydration reaction involving alkenes, we're basically just adding a water molecule to the structure, a hydrogen and hydroxy group to the two carbon atoms that are involved in the double bond. In the halogenation reaction involving alkenes, we're basically adding two halogen atoms to the structure. So two halogen atoms that are bonded to the two carbon atoms involved in the double bond. A hydration reaction is the complete opposite of dehydration reaction. So instead of removing a water molecule from a structure, we're adding a water molecule to the structure. And so the hydration of alkene molecules basically converts an alkene into an alcohol. So here's the reaction mechanism of a hydration reaction in which an alkene is converted into an alcohol. So the very first step is the reaction between the alkene and the hydronium ion. And this results in the formation of a carbocation. The second step is the nucleophilic attack, in which the water molecule is acting as a nucleophile, attacking this electron-deficient carbon atom. And this results in the formation of a sigma bond between the oxygen and the carbon atom, with a positive charge on the oxygen. The third step involves the deprotonation of this hydrogen atom. So water is acting as a Bronsted-Lowry base, deprotonating this hydrogen, which results in the cleavage of the sigma bond between the oxygen and the hydrogen atom. And the result is the formation of the final product, which is a cyclohexanol, and a byproduct, which is a hydronium ion. So the regeneration of this hydronium ion suggests that we have an acid-catalyzed reaction. Just like water, alcohols can also be added to alkenes, forming ethers by the same mechanism. So here we have methylpropene reacting with methanol in the presence of sulfuric acid. By the same mechanism, the methoxy group is added to the more substituted carbon atom, and then the hydrogen to the less substituted carbon atom. Here's practice problem number 21. What two alkenes give rise to each alcohol as the major product of acid-catalyzed hydration? So the first thing that I would do here is to identify the carbocation that was generated during the first step. And so what we have is a tertiary carbocation, as shown here. And so now all you have to do is place a double bond between this carbon atom that's electron deficient and any of these carbons adjacent to it. And so for the first alkene would be a double bond between this carbon atom and this carbon up top. And for the second alkene, it would be a double bond between this carbon atom and this third carbon right here. And so these two are the two alkenes that give rise to this alcohol. And for the second alcohol here, again, the very first thing that I would do is to generate the carbocation that's produced during the first step. And here's the carbocation. And then all you have to do now is place the double bond between the electron-deficient carbon atom and any of these adjacent carbon atoms. And so for the first one, we would have a double bond between the electron-deficient carbon atom and the terminal carbon. And the second one would be a double bond between this carbon atom and any of these two carbon atoms here. And they would produce identical molecules. And so we would have this double bond between the electron-deficient carbon and one of these carbon atoms here. And for the third alcohol here, we'll do the same thing. So we can have the carbocation on this carbon atom, and then we can connect a double bond between this carbon and this outside carbon atom here. Or a double bond between this carbon and this carbon right here. So now let's take a look at halogenation, which is the electrophilic addition of halogen to an alkene. And halogenation is essentially the addition of two halogen atoms to an alkene to form a vicinal dihalide. And so in this reaction, a pi bond is broken, and then two halogen atoms are bonded to the two carbon atoms that are involved in the double bond. So what we get here is a vicinal dihalide, in which the two carbon atoms or the two halogen atoms are in anti-position. So what we have here is an anti-addition. So down here we have two examples of halogenation reaction. The first one is a reaction between propene and chlorine gas. And so the pi bond between the two carbon atoms is broken. The sigma bond between the two chlorine atoms is also broken. And then two sigma bonds are formed between the carbon atoms and the chlorine atoms. So what we get here is a dichloride. And for the second reaction here, we have cyclohexene reacting with bromine gas. And again, the pi bond is broken between these two carbon atoms. The sigma bond is broken between the two bromine atoms. And then two sigma bonds are formed between the carbon atoms and the bromine atoms. So what we have here is a dibromide. And so if we're using a chlorine gas, then this process is known as chlorination. But if we're using bromine gas, the process is known as bromination. So here's a few things that you should remember regarding halogenation reaction, which is the electrophilic addition of halogen atoms to an alkene. Halogens add to pi bonds because halogens are polarizable, which means that their electron cloud can easily be distorted. Another way to put this is the electron-rich double bond induces or creates a dipole in a halogen molecule. And so one of the halogen atoms will have a partial positive charge, and then the other halogen atom will have a partial negative charge. So this is a temporary dipole that's induced by an electron-rich double bond. And so the electrophilic halogen atom is then attracted to the nucleophilic double bond, making electrophilic addition possible. And so because of this, halogenation actually follows a different reaction mechanism compared to hydrohalogenation or hydration. So here's some key differences. Carbocations are not intermediates in halogenation reactions. And so because of this, there's not going to be any carbocation rearrangement in halogenation reaction. And only anti-addition of the halogen atoms is observed. So here's the reaction mechanism for the addition of a halogen molecule to an alkene. So the first step here is the formation of the bridged halonium ion, which is extremely unstable because you have a three-membered ring here, which causes a lot of steric strain and angle strain. And so in this first step, you can see that there's a total of 4 bonds involved. A pi bond is broken, 2 sigma bonds are formed, and 1 sigma bond is broken. And this forms the bridged halonium ion, in which the halogen atom has a positive charge. And then the second step here is the nucleophilic attack. So the halide ion will act as a nucleophile attacking one of these carbon atoms, which results in the cleavage of the sigma bond between this carbon atom and this halogen atom. And so what we have is a vicinal dihalide. So here are some of the key differences and similarities between carbocations and bridged halonium ions. Carbocations are unstable because they only have 6 electrons, so they don't have a complete octet. On the other hand, bridged halonium ions are unstable because they contain a 3-membered ring, and so there's a lot of angle strain in this reactive intermediate. So before we look at some examples here, let's first take a look at the stereochemistry of halonium formation. So here we have the chlorination of cyclopentene, which results in formation of 2 enantiomers of trans-1,2-dichlorocyclopentane with 0 cis products. To explain this, we have to look at the reaction mechanism of this process. So the first step in this reaction is the formation of the halonium ion. In this case, we have a chloronium ion. These 2 chloronium ions are actually identical, because if you were to flip one of them about 180 degrees, you get the same exact ion. So these 2 chloronium ions are identical. And in the second step, we have the attack of the nucleophile. And the chloride ion is acting as a nucleophile, which can attack this chloronium ion on either side of the molecule. And so the chloride ion can attack on the right-hand side or on the left-hand side. And again, this can happen with equal probability. So that means that we're going to get two different molecules with equal concentration. And the two molecules are non-superimposable mirror images. So they are a set or a pair of enantiomers in which the two chlorine atoms are oriented trans to one another. And so if you put them in juxtaposition here side by side, the two chlorine atoms or the two molecules are non-superimposable mirror images. So what we get here is a racemic mixture. The halogenation of alkenes is known to be stereospecific. So what that means is that if we have two stereoisomers that are undergoing halogenation reaction, the products that they get are going to be completely different. So an example is shown here. We have the cis and trans butene isomers. And the cis butene undergoing bromination reaction will generate a pair of enantiomers. So we have a racemic mixture. On the other hand, the trans stereoisomer undergoing the same exact bromination reaction will generate a meso compound, which is completely different compared to the products generated by the cis isomer. Here's practice problem number 23. Draw the products of each reaction, including stereochemistry. So the first halogenation reaction here, we have bromination, in which two bromine atoms are added or bonded to the two carbon atoms involved in the pi bond. And so the first product that we get is this one right here, in which the two bromine atoms are in transposition. The other product will be a non-superimposable mirror image of this molecule. And so what we have is a racemic mixture. And for the second halogenation reaction here, we have chlorination, in which two chlorine atoms will be added to the two carbon atoms involved in the pi bond. And so this is the first product formed. And you can see that one of the chlorine atoms, the top chlorine atom, is oriented towards the front, and then the other chlorine atom is oriented towards the back. Again, we have a trans position here. The other product will be a non-superimposable mirror image of this molecule. And so again, we have a racemic mixture. And here's another practice problem. Draw all stereoisomers formed in each reaction. So the first halogenation reaction here is the chlorination of 1-methyl cyclopentene. So you can see that the chlorine atoms would be added to these two carbon atoms that are involved in the double bond. So the first product would look something like this, in which again the two chlorine atoms are in transposition. So this is one of the products. The other product has the chlorine atom, the top chlorine atom, oriented towards the front. And then the bottom chlorine atom will be oriented towards the back. And here it is. And so again, these two are enantiomers because they are mirror images and non-superimposable. And for the second halogenation here, the bromine atoms would be added to these two carbon atoms involved in the pi bond. And so the first product would look something like this, in which the top bromine atom is oriented towards the front, and then the bottom bromine atom is oriented towards the back. The second molecule would look something like this, in which the top bromine atom is oriented towards the back, and then the bottom bromine atom is oriented towards the front. But these two molecules right here are actually identical. They are one and the same. And the reason why is because this single bond right here can rotate. So if you were to rotate this bond right here, then the two bromine atoms are now oriented towards the back. And then over here, if you were to rotate this bond here, then the two bromine atoms will now be oriented towards the front. But then when you flip it 180 degrees, the two molecules will overlap each other. And so they are actually one and the same identical molecule. So we have a meso compound here. And for the third halogenation reaction here, again, these two bromine atoms would be added to these two carbon atoms involved in the double bond. And so the first structure would look something like this. Again, the two bromine atoms are in transposition. So this bromine atom right here on the right is in transposition with the methyl group. And then in the second product, you can see here that the left bromine atom is now in transposition with the methyl group. And so these two molecules are non-superimposable, non-mirror images. And so these two molecules are actually diastereomers. So the next addition reaction that we're going to take a look at is the formation of halohydrin from alkenes. And so if we break down the word halohydrin, halo is for halogen, and a hydrin is a hydroxy group. And so we're essentially adding a halogen atom and a hydroxy group to the two carbon atoms involved in the double bond. So here's the general chemical reaction equation for the formation of halohydrin. So here we have cyclohexene reacting with a halogen molecule in water. And so this reaction results in the addition of a halogen atom and a hydroxy group to the two carbon atoms that are involved in the double bond. So here are two examples of an addition reaction involving the formation of a halohydrin. So the very first step is the cleavage of the pi bond between the two carbon atoms involved in the double bond, and the cleavage of the sigma bond between the two halogen atoms in the halogen molecule. And this results in the addition of the halogen atom. In addition, we also have the cleavage of the sigma bond between the oxygen and one of the hydrogen atoms, which results in the formation of the hydroxy group, the sigma bond between the carbon and the oxygen in the hydroxy group. So what we have is a halohydrin. Here's the reaction mechanism. So the very first step is the formation of the bridge halonium ion, which is the rate determining step. In this first step, the pi bond is broken, and then two sigma bonds are formed between the two carbon atoms and one of the halogen atoms, and then the sigma bond is broken between the two halogen atoms in the molecule. And again, this results in the formation of the bridge halonium ion. The second step here is the attack of the nucleophile. So because water is at a higher concentration than the halide ion, water is acting as a nucleophile. So it will attack one of the carbon atoms, which results in the cleavage of the sigma bond between the carbon atom and the halogen atom. And so what we have here is the addition of the halogen and a water molecule. And then for the third step here, water molecule will act as a base, deprotonating this hydrogen that's bonded to this oxygen atom. And so this results in the cleavage of the sigma bond between the hydrogen and the oxygen atom, which again results in the formation of the final product, which is the halohydrin. So the formation of this halohydrin is sort of similar to the halogenation process, in which the halogen and the hydroxy group are in anti-position. So bromohydrins can be generated from alkenes by the combination of liquid bromine and water molecule. Other reagents can also be used. For example, NBS, which stands for N-bromosuccinimide in aqueous DMSO. So this is the structure of N-bromosuccinimide. So here we have a transalkene that reacts with NBS in DMSO, in aqueous DMSO. So what we have here is the formation of bromohydrin, in which the bromine atom and the hydroxy group are in anti-position. And as I mentioned earlier, the halogen atom and the hydroxy group are added to the two carbon atoms via anti-addition. And the reason behind this is because the bridge halonium ion is opened by a nucleophilic backside attack. So here's another example. We have cyclopentene reacting with bromine in water. So because the bromine atom and the hydroxy group are added to the two carbon atoms via anti-addition, the two groups are going to be in transposition. And so in this example, we get two enantiomers of the molecule. So what we've seen so far is the halohydrin formation for symmetrical alkenes. But with unsymmetrical alkenes, it's a little bit different. It's different in such a way that the preferred product actually has the halogen atom bonded to the less substituted carbon, and then the nucleophile or the hydroxy group is bonded to the more substituted carbon atom. So here we have an unsymmetrical alkene undergoing addition reaction. So what we get here is a product in which the hydroxy group is bonded to the more substituted carbon atom, and then the halogen atom is bonded to the less substituted carbon atom. And this is the only product that's formed by this addition reaction. And so, again, the reason why is because during the second step, the hydroxy group, or the water molecule, which is acting as a nucleophile, attacks the more substituted carbon atom and not the less substituted carbon. And so again, the nucleophilic attack occurs at the more substituted carbon because that carbon is better able to accommodate the partial positive charge in the transition state. So here's the reaction mechanism. Again, we have the unsymmetrical alkene here, and the first step is the formation of the halonium or bridged halonium ion. And then the second step is the attack of the nucleophile. So water is acting as a nucleophile, which would then attack the more substituted carbon atom, resulting in the cleavage of the sigma bond between the more substituted carbon and the halogen atom, followed by deprotonation of this hydrogen. And so again, water this time will act as a base, which would deprotonate this hydrogen, resulting in the cleavage of the sigma bond between the hydrogen and the oxygen atom. And so the final product is a bromohydrin. Again, the bromine atom and the hydroxy group are in anti-position. So here's a table that summarizes the conversion of alkenes to halohydrins. In terms of mechanism, the mechanism involves 3 steps. The first step is the slow step, which is the rate determining step. And this results in formation of a bridged halonium ion. And so since we don't have a carbocation that's formed, there's not going to be any rearrangements. The second step is the nucleophilic attack, and then the third step is deprotonation. In terms of regioselectivity, the electrophile or the halogen bonds to the less substituted carbon atom, and then the nucleophile or the hydroxy group bonds to the more substituted carbon. And in terms of its stereochemistry, we have an anti-addition, meaning that the hydroxy group and the halogen are in anti-position. So here's an example. Draw the products of the following reaction, including stereochemistry. So we have the addition reaction of transbutene in liquid bromine and water. So the very first step here is the formation of the bridged halonium ion. So in this case, we have bonds that are breaking and bonds that are forming, which results in the formation of the bromonium or the bridged bromonium ion as shown here. And then the second step is the nucleophilic attack. So water can attack either carbon atom because they are equally substituted. And so the water can attack this carbon atom on the left or the carbon atom on the right. And so there's going to be a cleavage of the sigma bond between the carbon atom and the bromine atom. And so the result is the formation of the halohydrin, in which the bromine atom is oriented towards the front, and then the hydroxy group is oriented towards the back. And so again, both groups are in anti-position. And since the water molecule can attack on either side of the bromonium ion, we're going to have an enantiomer here. And so if the water molecule attacks this carbon atom via backside attack, then it will be oriented towards the back. But if the water molecule attacks this carbon atom, then it's going to be oriented towards the back, and it's going to be the mirror image of this molecule here. And so it's going to be an enantiomer. It's going to be a pair of enantiomers. And here's practice problem number 25. Draw the products of each reaction and indicate their stereochemistry. So for the first addition reaction here, you can see that we have a symmetrical alkene reacting with N-bromosuccinimide in DMSO, in aqueous DMSO. So that means that we have a source of bromine atom here. And so if you're not showing the chemical reaction mechanism, what you can do is locate the double bond. This is basically where the bromine atom and the hydroxy group will be bonded to. And so here's the halohydrin. So we have, again, you don't have to put the bromine atom to this carbon atom. You could be down here at the bottom and the hydroxy group up top. It doesn't really matter. So here we have the bromine atom bonded to the top carbon atom, and then the hydroxy group to the bottom carbon atom. And when you analyze these two carbon atoms here, they're stereogenic. And so that means that we're going to have stereoisomers. And so since we have addition reactions, the groups, the bromine atom and the hydroxy group, will be added to the carbon atoms in an anti-fashion. Right? So we have anti-addition. So that means that the bromine atom will be on the opposite side of the molecule, and hydroxy group will be facing towards the back. So we have the bromine atom facing towards the front, the hydroxy group towards the back. And so this is, again, anti-addition. And so the other possibility is that we have the bromine atom facing towards the back and the hydroxy group facing towards the front. So this is the other possible stereoisomer here. So we have two products, a pair of enantiomers. So these two molecules are non-superimposable mirror images, and so they are a pair of enantiomers. So in that case, the product of this reaction is a racemic mixture. And for the second addition reaction here, you can see that we have an unsymmetrical alkene. And so that means that the nucleophile will attack the more substituted carbon, and then the halogen will be bonded to the less substituted carbon atom. And so in this case, the water molecule, which is the nucleophile, will attack this carbon atom right here. And so we're going to have a hydroxy group bonded to this more substituted carbon. And then the halogen, the chlorine atom, will be bonded to the less substituted carbon. And so in terms of stereochemistry, we're going to have to look at the anti-addition, right? So the hydroxy group and the chlorine atom will be bonded to the two carbon atoms in an anti-fashion. And so we can arbitrarily set the stereochemistry here. So we can set the hydroxy group to be facing towards the front, and then the chlorine atom to be facing towards the back. And so you can see that they are in transposition because of anti-addition. And so this is one of the products. And the other product would be one in which the hydroxy group is facing towards the back, and then the chlorine atom will be facing towards the front. And so when you analyze the two molecules here, you can see that they're actually non-superimposable mirror images. So when you flip this 180 degrees, then you can see that they are mirror images and they are non-superimposable. And so what we have here, again, is a mixture of enantiomers, a racemic mixture. And the last type of organic chemical reaction that we're going to take a look at involving alkenes is known as hydroboration oxidation. So this is a two-step process. The first step is hydroboration, and the second step is oxidation. So hydroboration oxidation is the conversion of an alkene into an alcohol. And this involves two steps. The first step is called hydroboration, and hydroboration is the addition of borane into the alkene to form this alkylborane molecule. And then the second step is the oxidation process. The carbon to boron bond of the alkylborane is converted to a carbon to oxygen bond, which forms the alcohol. The hydroboration oxidation process is very similar to the hydration reaction, in the sense that they both convert an alkene into an alcohol. The only difference is, unlike the hydration process, the hydroboration oxidation reaction does not involve the formation of a carbocation, which also means that there's not going to be any carbocation rearrangement. So first, let's take a look at hydroboration, which is the first step in the conversion of an alkene into an alcohol. And this involves borane, a reactive gas that exists mostly as a dimer, diborane, with the chemical formula B2H6. Borane is a strong Lewis acid, and it reacts pretty easily with Lewis bases such as THF. And so in the lab, BH3 or borane is commonly used as a complex with THF. So again, the first step in the conversion of an alkene into an alcohol is the conversion of an alkene into an intermediate known as alkylborane. So this process is known as hydroboration. So here's the reaction mechanism for the first step, which is hydroboration. You can see here that this involves a concerted reaction, which means that it all happens in a single step. There's no reactive intermediate, there's no carbocation involved. In this reaction, you can see that a pi bond is broken between the two carbon atoms involved in the double bond. A sigma bond is broken between the hydrogen and boron, and then two sigma bonds are formed. One between the carbon and the hydrogen atom, and the other one is between the carbon and the boron atom. And notice that the hydrogen and the BH2 are added on the same side of the molecule. So this is syn addition. Here we have the transition state. A pi bond is partially broken between the two carbon atoms. The sigma bond is partially broken between the hydrogen and boron atom. And then two sigma bonds are partially formed. One is between the carbon and the hydrogen, and the other one is between carbon and the boron atom. Again, this is the transition state. And because four atoms are involved, the transition state is said to be four-centered. So when you look at the chemical formula and chemical structure of borane, you can see that this molecule contains 3 boron to hydrogen bonds, which means that a single molecule of borane can react with 3 alkene equivalents. So the first reaction yields an alkylborane, the second reaction yields a dialkylborane, and then the third reaction yields a trialkylborane. And so we often draw hydroboration as if the addition stopped after only one equivalent of alkene reacts with one borane molecule. But in reality, what we get is a trialkylborane, in which the boron atom is bonded to 3 carbon atoms to form the trialkylborane molecule. Since only a single boron to hydrogen bond is needed for hydroboration, commercially available dialkylboranes having the general structure R2BH are sometimes used instead of borane, BH3. So one common example is 9BBN, and this is the structure of 9BBN. As you can see, there's only one single boron to hydrogen bond shown here in this molecule, and this is abbreviated with the symbol R2BH. When it comes to unsymmetrical alkenes, the boron atom bonds to the less substituted carbon atom. And the reason behind this is because of steric hindrance. The boron atom is relatively larger compared to a carbon atom, and so it bonds to the less sterically hindered, more accessible carbon atom. So here's an example. We have a propene molecule reacting with borane. So you can see that this carbon atom right here is the more substituted carbon atom that's involved in the double bond, and the one on the right hand side is the less substituted carbon. And so the borane molecule, the boron atom in the borane molecule, would attack this less substituted carbon atom as shown here, and this is the only product that's formed in this chemical reaction. The one on the right is not formed because this boron will never bond to this more substituted carbon atom because of steric factors. Another way to explain this regioselectivity in hydroboration is via electronic factors. So in the transition state, the boron bears a partial negative charge, and then the carbon bears a partial positive charge. And so the carbon bearing the partial positive charge should have more substituents bonded to it because these alkyl groups can stabilize the positive charge better. And so in other words, the more stable transition state has the partial positive charge on the more substituted carbon. Remember that these alkyl groups are electron donating groups, and again, they are able to stabilize a positive charge. So here's a schematic diagram showing you the hydroboration of an unsymmetrical alkene. So here you can see the transition state, which is four-centered, involving 4 atoms. And you can see here that the carbon atom bearing a partial positive charge is the more substituted carbon atom. And then the boron, which bears the partial negative charge, is bonded to the less substituted carbon atom. And so what we get here is an alkylborane in which the boron is bonded to the less substituted carbon. So here's practice problem number 26. What alkylborane is formed from the hydroboration of each alkene? So for the first one here, you can see that we have an unsymmetrical alkene. So that means that the boron atom will bond to this less substituted carbon. And so the BH2 is going to be bonded to this less substituted carbon atom, as shown here. And for the second one here, you can see that we have another unsymmetrical alkene. And so that means that the boron atom will be bonded to this less substituted carbon. And so again, the BH2 will be connected to this less substituted carbon atom, as shown here. And for the third one, another unsymmetrical alkene here. So that means that the boron atom will be bonded to this less substituted carbon on the right, as shown here. The hydroboration reaction is immediately followed by the oxidation reaction, in which the alkylborane is converted into the alcohol. So you can see that this oxidation process replaces the carbon to boron bond with a carbon to oxygen bond. So in this reaction over here, you can see that this oxidation reaction can be performed in a basic solution of hydrogen peroxide. So this alkylborane right here will undergo oxidation in a basic hydrogen peroxide, yielding this final product, which is the alcohol. And this results in formation of the alcohol with a retention of its configuration. And so in other words, the overall result of this hydroboration oxidation reaction is the syn addition of hydrogen and the hydroxy group to the double bond in an anti-Markovnikov fashion, meaning the hydrogen is bonded to the more substituted carbon and the hydroxy group is bonded to the less substituted carbon atom. So let's take a look at this one example here. Draw the product of the following reaction sequence, including stereochemistry. So here you can see that we have an unsymmetrical alkene. So you would expect this hydroboration oxidation reaction to yield an alcohol in which the hydroxy group will be bonded to the less substituted carbon atom, and then the hydrogen bonded to the more substituted carbon atom, which is an anti-Markovnikov addition. And because the hydroboration oxidation reaction always results in a syn addition of the hydrogen and the hydroxy group, you would expect the two groups to be on the same side of the plane. And here's one of the products of this hydroboration oxidation reaction, in which the hydroxy group is bonded to the less substituted carbon atom and the hydrogen bonded to the more substituted carbon. And you can see that they are added in a syn fashion, meaning that they are on the same side of the plane. And shown here is the second product of this reaction, in which the two groups are oriented towards the back of the molecule. And again, this is an anti-Markovnikov syn addition, because the hydrogen is bonded to the more substituted carbon and the hydroxy group is bonded to the less substituted carbon atom. And when you analyze these two structures here, you can see that they are non-superimposable mirror images, which makes them enantiomers. So this is a racemic mixture. Here's practice problem number 27. Draw the products formed when each alkene is treated with borane followed by basic solution of hydrogen peroxide. Include the stereochemistry at all stereogenic centers. So here's the first product. Again, the hydroxy group is bonded to the less substituted carbon, and then the hydrogen to the more substituted carbon atom. And in terms of stereochemistry, this is the second product of this chemical reaction. You can see that the hydroxy group and the hydrogen atom are oriented towards the back. And so these are the two products of this chemical reaction. And as you can see, they are non-superimposable mirror images. And so what we have here is a racemic mixture. And for this second unsymmetrical alkene here, you can see that this carbon atom right here is the more substituted carbon, and then the carbon on the left is the less substituted one. And so you would expect the hydroxy group to bond to this less substituted carbon atom, and then the hydrogen to this more substituted carbon. And so again, the addition of the two, the hydrogen and the hydroxy group, are via syn fashion. And so that means that they are oriented or bonded on the same side of the molecule. And so here's the first product. So you can see that the hydrogen and the hydroxy group are on the same side of the plane. And the second product in terms of stereochemistry would have the hydrogen and the hydroxy group oriented towards the back. And finally, for this molecule shown here, you can see that the more substituted carbon is this one up top, and the one at the bottom is the less substituted one. So again, the hydroxy group will bond to this carbon atom in an anti-Markovnikov addition, and then the hydrogen to the more substituted carbon atom. And so the first product is shown here. So you can see that the hydroxy group and the hydrogen atom are facing towards the front. And so this is via syn addition. And the second product is shown here. And now you can see that the hydrogen and the hydroxy group are oriented towards the back. And these two molecules right here, when you analyze their structures, you can see that they are not enantiomers, but rather diastereomers, meaning that they are non-superimposable, but not mirror images of one another. And so that's the very definition of diastereomers. And here's another practice problem. What alkene can be used to prepare each alcohol as the exclusive product of a two-step hydroboration oxidation sequence? So for this first alcohol right here, how do we generate this alcohol from an alkene? And so the first thing that I would do here is to remove or get rid of this hydroxy group right here, and then form the double bond between this carbon atom and the more substituted adjacent carbon atom, which is this one right here at the bottom. And so we're going to form a double bond between them. And so the alkene in which we can generate this alcohol from is shown here. So this is what the alkene looks like. So if you were to react this via hydroboration oxidation reaction, you would have the hydroxy group bonded to the less substituted carbon atom, and then the hydrogen bonded to the more substituted carbon. And for the second alcohol here, we would do the same thing. So we would remove this hydroxy group right here, and then form a double bond between this carbon atom and the more substituted adjacent carbon atom, as shown here. So you can see that, again, if this undergoes hydroboration oxidation reaction, you would expect the hydroxy group to be bonded to the less substituted carbon atom, and then the hydrogen to the more substituted carbon. And finally, for this third alcohol here, you would remove this hydroxy group and then form a double bond between this carbon atom and the more substituted adjacent carbon atom. And so this is the alkene product. Again, if this undergoes hydroboration oxidation reaction, you would expect the hydroxy group to bond to the less substituted carbon and the hydrogen to the more substituted carbon atom. And here's the table that summarizes the hydroboration oxidation of alkenes. In terms of mechanism, the addition of the hydrogen and the BH2 occurs in a single step. So it's a concerted reaction. And since there's not going to be any carbocations generated, there's not going to be any carbocation rearrangements. And in terms of regioselectivity, the hydroxy group bonds to the less substituted carbon atom and the hydrogen to the more substituted carbon in an anti-Markovnikov addition. And finally, in terms of stereochemistry, we have a syn addition, and the hydroxy group replaces the BH2 with retention of configuration.